Welcome everyone to this DLC webinar on interoperability for network lighting controls. My name is Levin Nock. This presentation will give you an overview of a research report that DLC recently published on our website at designlights.org. In terms of interoperability in network lighting controls, this slide summarizes the DLC's vision. Why are we working on this topic? Well, we believe that interoperable network lighting control systems will enhance the market value of NLC systems in multiple ways. They will make buildings more energy efficient and occupants more comfortable, as appropriate lighting and thermal comfort is delivered when and where it's needed. They will make facility operations more efficient because bidirectional data sharing enables facility managers to monitor operations more closely. These and other benefits delivered by ever-expanding new software applications will increase market adoption, thus saving more electricity, which is the DLC's core mission. As I mentioned, my name is Levin Nock. As a senior technical manager at the Design Lights Consortium, I manage development of the DLC list of network lighting control systems that are eligible for efficiency incentives from most DLC member utility programs. This database enables specifiers to choose an appropriate NLC system for each of their commercial lighting projects. Joining me today are three esteemed colleagues who have been researching interoperability for the DLC. We will each present a section of the webinar. Dr. Yaojong Wen is a senior engineer at Energy Solutions, where he leads technical research on energy and non-energy benefits of connected devices and systems, including network lighting controls. Yao has provided technical support on several DLC policies and previously worked as a research scientist at a major lighting company, where he focused on advanced lighting control technologies and was involved in several lighting system standardization activities. Ron Bernstein is CEO and Chief Engineer of RBCG Consulting, providing consulting services primarily for large end users and owners focusing on building automation control networking, system design, and spec development. He has over 35 years of experience developing interoperability standards, promoting open systems, and providing integration support for industrial, commercial, and residential automation and controls applications. He holds a BS in mechanical engineering, a master's in psychology, and a master's in philosophy, three cornerstones of his consulting practice. Michael Poplawski joined PNNL in 2009 as a senior engineer following 12 years in the commercial semiconductor industry, where his work experience included device engineering and reliability, circuit design, application support, and technical marketing. His current research efforts, supported by the Department of Energy's solid-state lighting program, are focused on evaluating and characterizing new connected lighting system technologies and capabilities, exploring the potential for connected lighting systems to provide grid services, and the development of related standards and specifications. Michael is a member of IES, IEEE, and ASHRAE, serves on multiple standards development committees, and consults with numerous energy efficiency organizations, specification bodies, and early adopters. On the agenda for today, I am giving the introduction, and then Yao will give an overview of the research that was conducted. After that, we'll dive into more details about three use cases, or ways that interoperable network lighting controls can be used for particular purposes. After that, Yao will summarize which puzzle pieces are missing from current practice and how those gaps can be bridged. And then we will conclude with next steps for the future. Because we have a relatively large audience today, everyone is muted. If you have questions about the topics being discussed, please write them in the questions pane, and we'll do our best to answer them either in the questions box with text or in a time for questions at the end of the webinar. If you have comments about logistics or discussion for the audience, please use the comments pane. Now I'll give a brief introduction to the topic of interoperability. In order for buildings to operate efficiently while keeping their occupants comfortable and playing nicely on a modern electric grid powered by renewable energy sources, we need buildings to operate with built-in intelligence, constantly gathering data and taking action based on that data, with various systems within and beyond a building acting together in a coordinated way. The ability to communicate and exchange actionable information is called interoperability. In practically all occupied commercial spaces, luminaires are evenly distributed overhead across the space, along with a convenient source of electrical power at each luminaire, as shown in this floor plan with a wiring diagram of the overhead luminaires. This makes networked luminaires ideal for supporting intelligent buildings, with integrated sensors not only for occupancy and light levels, but also air quality and other parameters of occupant comfort and safety. However, all that sensor data is only useful if information can be exchanged between various systems so that one system can gather the data and other systems can act upon it. This webinar and the report it's based on are organized in terms of use cases. A use case describes a scenario where a system is used to achieve a specific goal or goals. For instance, in one of the use cases we'll explore in a few minutes, an NLC system is used to generate an energy report that is delivered to an energy efficiency program, supporting an incentive payment that covers some of the cost of the NLC system. The main goal of the building owner is to reduce the electricity bills and the cost of the NLC system, while the main goal of the efficiency program is to save electricity. A use case defines a series of interactions between an actor, in this case, the NLC system creating the energy report, and another actor, in this case, the utility efficiency program receiving the energy report. The NLC system sends specific data along specific communication pathways in order to meet the goals of the building owner and the utility. The diagram here shows the NLC system in the upper left corner interacting with various systems within a building on the right. Within a building on the left and beyond the building on the right. And now, Dr. Wen will describe the research that was conducted to support expanding interoperability in network lighting controls, as soon as I give him mouse control, which he should have now.
Thanks, Levin. So the objectives of this research was to identify critical interoperability use cases. These are the use cases that can create high value to the stakeholders in the form of increased energy savings, improved operational efficiencies, improved occupant satisfactions, etc., and also be technologically feasible in the time frame of 3 to 5 years. The research also aimed to identify key interventions that can advance these critical interoperability use cases, as well as the opportunities for the DLC to accelerate adoption of NLC interoperability. Here's a high-level description of the research methodology we developed for this study. We first developed a use case catalog, which contained 32 specific use cases across all sectors. This use case catalog is included as an appendix in the report. We then identified metrics, mostly qualitative, for evaluating and prioritizing the use cases. These metrics include market size, energy and cost savings potentials, performance enhancements such as the potential for improving operational efficiencies, boosting occupant comfort, or even increasing revenues, and the technical feasibility. We also conducted phone interviews and online surveys to collect stakeholders' input on these use cases. And after assessing the use cases along the qualitative metrics and incorporating stakeholders' opinions, we narrowed down to 3 critical interoperability use cases. And these 3 use cases are in the high-level categories of external systems integration, load shading demand response, and energy monitoring. We then performed an in-depth analysis on these 3 use cases which will be the focus of the remaining of this webinar. A bit more details on the research methodology discussed in the previous slide. These are the 6 stakeholder groups that we considered and engaged in each step of the research. So they are end users, including building owners, managers, operators, as well as real estate portfolio managers. Specifiers, including designers, engineers, and architects, contractors and energy consultants, manufacturers, integrators, and value-added service providers, and the utilities. And here are the aspects we investigated in the in-depth analysis for each of the 3 use cases. They are discussed in great detail in the full report, but in the interest of time, we will only highlight notable findings in the subsequent sections of this webinar. Again, external systems integration, load shedding, demand response, and energy monitoring are the 3 use cases identified as our initial focus for NLC interoperability and for the in-depth analysis. I will now hand over to Ron to dive into the use case of external systems integration. Ron?
Okay, thank you. Yeah, I appreciate being here and being able to talk about this. So for this use case, we looked at the lighting systems and how they can interface to external systems within the building and beyond. We researched the interoperability requirements and the potential cross-domain mutual value propositions. So we'll talk about this external systems interface through the next few slides. So use case number 1, this, move my slide ahead here. Yeah, so this relates to how lighting systems can produce a wealth of information from their embedded sensors and controllers. So use case number 1 focuses on the NLC's components. That includes the sensors, the luminaires, the controllers that can be shared to non-lighting systems. Primarily, this focuses on the sensors associated with the lighting controls, including occupancy. Occupancy of a zone can help other systems, such as the HVAC system, adjust air temperature and flow in a space. So I've seen HVAC system integrators install parallel occupancy sensors in the same space as the lighting system. In addition, newer multi-sensors can even provide more information, such as presence and absence, occupancy density, daylighting, indoor air quality, and even traffic flow and directionality. This information may be very beneficial to other building applications, including the security and life safety system, the elevator control system, and certainly the HVAC system. In order for the NLC to share this data, a strong interoperability model is required that defines how that data will be shared, and the API developer has the context needed to turn the raw sensor value into actionable information. So in this example, we're talking about how the sensor data needs to parallel the lighting zone with the HVAC zone. And some of the primary benefits of this will be the operator will benefit from higher operational efficiencies and lower equipment installation costs, and certainly energy savings, not to mention the reduction in duplicate sensors. So this is an example in this use case of where interoperability is between one system in the building and another system in the building, where there's a common control and communication network. We'll see from other interoperability models in other use cases that there's beyond the building and certainly with the utility as well, but this one focuses here within the building and the various building systems. There's a requirement that the lighting system and, say, the HVAC system have a communications path enabled such that messages can be shared between those 2 different systems. Let's talk a little bit about the barriers and the market status. This key use case of sharing information from the lighting system to other systems not very widely used today in the US market, mainly because of the approach of system developers where there's a siloed system between the lighting system and, say, the HVAC system. They're typically designed in a silo and they're implemented in a silo. And then maybe as an afterthought, there's some cross integration. So as mentioned, we're seeing more duplication of sensors in each domain rather than the system sharing cross domain. However, approximately 45% of the DLC listed lighting systems can provide this information today via an API. Personally, I expect this number to grow as this use case becomes more mainstream. To me, it's an obvious opportunity for improved efficiency. And then some barriers and challenges include the lack of consistent representation of occupancy status exposed through the API across the NLC. So this includes things like mapping the lighting zones and the thermal zones, things like temporal and spatial data granularity, updating and reporting frequency, and the big one is the data format inconsistencies. So just as an aside, I'm working on a project now with a large international retailer that is addressing this use case directly and has developed a complete set of requirements for lighting system interoperability, as well as HVAC and refrigeration. In this project, the owner needs better visibility into the stores as a way of monitoring and controlling energy. With over $1 billion of annual energy costs, every effort is being made to control the environment. Knowing the occupancy density can provide a means to potentially dim the lighting systems in certain zones, and as occupancy increases, adjust accordingly. This application integrates the lighting system with the energy management system to improve efficiency. So there are a variety of leadership and support activities happening in the market. Let me cover a couple of them for you. Okay, somebody's moving the mouse. All right, there we go. So the DLC is taking a leadership role in addressing this opportunity by enhancing the qualified products technical requirements that address cross-system data sharing through better interoperability definitions. There's some great work being done in a variety of the trade associations and even with the US labs such as PNNL. ASHRAE has several initiatives to help with integration of systems within the building. While ASHRAE has its focus in HVAC and refrigeration, there are several projects underway to bridge these gaps. And PNNL, under contracts with the US Department of Energy, is working to bridge and enhance the adoption of network lighting systems to validate the value of better integration across these many systems. But it really starts with the owner that has to develop a plan and a need. Some encouragement from public policy and codes is helping, including California Title 24 requirements, which relates to energy efficiency. And that leads us to the next use case. Yeah, let me turn it back over to you.
No, actually, Michael's taking the next one.
Oh, I'm sorry. Okay, Michael, you're on the next.
Okay, so you're going to give me control.
I think you gave Michael screen share rather than mouse control.
That's what it looks like.
Bear with
Sorry
us.
about that. Make presenter.
We want to give him mouse control, not make presenter.
Are we back to the leadership and supportive interventions?
Yes.
Okay, and Michael should have mouse control.
Nope.
Okay, well then I will.
Why don't you just move the next slide so we can keep going?
Yeah. Oh. There, try again. There we go.
Okay. So our next use case, as described in the report, is load shedding and demand response. But really, it's about grid service even beyond load shedding and demand response. So let's talk a little bit about that. This use case facilitates two-way communication between a lighting system or a building with lighting systems, and potentially one of many entities that are set up to provide grid services beyond peak load reduction. Those entities might be the grid operator itself, might be an energy aggregator, might be an on-site distributed energy management system, or microgrid. In those latter cases, those entities would be communicating directly with the grid operator. And by grid services beyond peak load reduction, really we're contrasting the historical use of demand response to reduce peaks and eliminate the need or reduce the need for utilities to turn on expensive peaking generation sources. But increasingly, as renewable energy sources are integrated into the grid, their intermittent nature creates additional needs, and in many ways more complex needs than just reducing peaks. And meeting these needs in the most efficient and frankly cost-effective way requires two-way communication, or is anticipated to require two-way communication. So in such a scenario, the lighting system or the NLC might do all of the following, right? It might assess occupant needs in quasi real time, if not real time, and communicate its load flexibility again to the grid or to one of the other aggregating type entities. And it might do that at any point in time. It might also receive grid requests or incentives. Incentives could be in the form of prices, energy prices, and modify its energy consumption and power demand to meet grid needs. And finally, report the changes it made, right? Report the changes in power demand or energy consumption that resulted from its modifications. There are many ways, again, that this could be implemented, and the diagram here just kind of shows one example where maybe a lighting system is just one of multiple systems in a building that are enabled or configured to provide grid services, and where the grid service is coordinated by an on-site energy management system. But that's just one example of how this could be done. So here, getting into a little more detail of that example, right? The grid service request is dispatched to the energy management system in the building, and what's requested is an estimate to which the building could commit at some future point in time. So the EMS, as the communicating entity, might poll or talk to each subsystem, including the lighting system, and request predicted load shed capacity at, again, some future point in time. The EMS would then respond back to the grid administrator. That would enable the grid administrator to pick its best path forward and then create an actual dispatch event. During such an event, the EMS might continue to pull the real-time power demand and energy consumption from all the end-use systems, including the lighting systems, and report both in real time and upon conclusion or final delivery, the overall building performance to the grid administrator, upon which point financial settlement could occur. So again, the real value here is for utilities or grid operators to keep their energy procurement costs low and return the savings to customers as program participation incentives. So this is an example of interoperability beyond a building, right? Where a lighting system is communicating, again, maybe directly, maybe through an intermediary to a grid operator. In this case, described as a utility demand response program. So let's talk about perceived market status and barriers here. So, of course, demand response programs have been out for a while. Some are fairly mature, but in the current standard practice, lighting loads either rarely participate or do so very modestly when they do. And the reason is because typically these programs are direct control dispatch. And in order to manage the risk of not meeting occupant needs at a certain point in time, lighting systems are configured or enrolled to, again, perform very modestly, maybe just dimming lights 10%. So this, limits the participation and impact lighting systems can provide today. However, there are existing DR protocols such as OpenADR that already support two-way communication and more sophisticated scenarios, but they're not really well fleshed out or implemented in the real world in actual retail programs yet. That's starting to change in various pilots and other emerging efforts. In terms of the state of current technology, 62% of NLCs on the DLC can receive some form, can directly receive and comprehend, if you will, some form of DR dispatch signal. Typically, this is OpenADR. 15% of listed NLCs can report their real-time power demand and energy consumption. Market barriers and technical challenges. I think in many ways this is a little bit of a chicken and the egg scenario where lighting systems aren't participating a lot right now due to risk, needs to manage risk and the lack of two-way communication. And pilots need to establish how that would work, but those challenges are preventing or have slowed the development of pilots and broad-scale adoption. I think related to that is the lack of well-defined and proven strategies for assessing occupant needs in any form of real time, if you will, and using them to communicate load flexibility in varying future timeframes. So, here is a role for things like occupancy, maybe, and other sensors to facilitate the assessing of occupant lighting needs, and again, being able to use them to determine and communicate load flexibility. So supporting interventions, here is really some both ongoing activities and maybe suggestions for increased or new activities. Manufacturers and energy scientists, I think, can provide guidance for assessing, again, and communicating lighting load flexibility in varying future timeframes for specific lighting applications, building types, and prioritizations. One keynote, again, when people talk timeframes, traditionally DR programs have, have been set up at the event level where maybe there's an unknown when the event's going to happen, but there's a limited number of events that would happen per year. But increasingly, grid services mean, I have forewarning and that the event's going to happen, and I'm communicating that. And the time frame may range from days to hours to even in some cases seconds. So it's a more specific and widely varying time frames that we're talking about here. Related to communicating flexibility, lighting scientists and specifiers, can provide guidance for assessing and communicating occupant lighting needs, again, in varying time frames, and again, for specific lighting applications, building types, and prioritizations, all of which I think many of us know vary and today, vary today in terms of applications and building types, but prioritization may vary in the future, right? Even within a given application, right? All users of a particular, big box retail store or bank or whatnot might have different prioritizations based on their, financial needs and occupant needs. Utilities can integrate energy efficiency and their, existing or emerging load shed or demand response or increasingly grid service programs and conduct pilot programs that utilize two-way communication. So this is really, suggesting building upon the existing relationships with end users that maybe are in silos in terms of energy efficiency and traditional LSDR, and kind of integrating them together and presenting opportunities in a consistent, single channel, if you will. Trade associations, of course, will be needed to develop training to configure NLC for these new purposes, right? This, we imagine, is, can build upon the existing capabilities that exist in NLC for configuring them, but maybe requires some new capabilities, in particular capabilities that allow you to prioritize maybe which lighting devices should participate or when they should participate, or both. And finally, from a policy standpoint, right, standards development organizations could standardize NLC reporting accuracy and other requirements for these purposes. and standardized protocols and data models for, again, communicating load flexibility and response across building systems. And with that, do I still have? I think you've taken it back, right? So with that, I think we're going to move on to our third use case. There we go.
Okay, thanks, Michael. So the third use case is about energy monitoring. And at a high level, the definition of the energy monitoring use case is that lighting system energy data is reported by the NLC and shared with authorized entities over the internet. A specific example we highlighted for the analysis is the case where a utilities energy efficiency program requires the NLC to report energy data at a 15-minute interval over a certain period of time, such as 1 year. The energy data is then transmitted to the utilities repository in an automatic fashion over the internet at a regular interval, for example, transmission of every week or every month. And the energy data from the program participants is used to verify the energy performance of individual systems, which of course are paid for partially by the utility incentives, and also to assess the program level effectiveness and cost benefit. There are, of course, value for each stakeholder groups, and the primary value of this example would be to allow the utilities to claim more accurate program savings, to streamline program implementation, and thereby providing customers with higher incentives. And therefore, the customers will be the ones who can get the most out of the NLC system. Going back to the graph we have seen a few times today, this is another example where NLC interoperability goes beyond the boundary of a building. So requiring NLC to report energy data is already being implemented in a much simplified form by several utilities. And here is a list of DLC member programs we identified that already require NLC energy data reporting. Some of the programs require submission of NLC energy data to be eligible for the incentive programs. One program, for example, lists energy reporting in an interval of 15 minutes or less as a minimum system requirement for program participation. And other programs provide add-on incentives or higher amount of incentives if the program participants choose to report the NLC energy data to the utilities. For instance, one particular utility provides up to 40% more incentives if the NLC installation is capable of energy monitoring and if the customers are willing to share the data with that utility. Now, the common practice of the utility programs we mentioned in the previous slide is to mostly rely on the energy data in CSV format, often directly exported from the NLC dashboard and submitted by the program participants. The data is then parsed manually by the program implementers to perform spreadsheet-based energy savings calculations and verifications. All in all, this is very labor intensive and not necessarily a very scalable approach. And in terms of current product support, based on the features listed on the DLC QPL for NLCs, 87% of the products already support energy monitoring and reporting in various capacities. However, only 21% of the products support access to historical energy data through an application programming interface or an API, which is one of the key enablers for automatic energy data intake to fully realize this use case. So One of the main barriers is inconsistent data access and reporting format, both on the NLC system side and on the utility side. Without NLC supporting a consistent data access and reporting format, utilities are having a hard time defining their data requirements. On the other hand, without clear data access and reporting requirements across utilities, NLC manufacturers may be challenged to build in the necessary functionalities to support the use case. Moreover, there is also a lack of standardized automatic data intake mechanism and process that the utilities can follow. So to help advance the state of this interoperability use case, here are some of the promising supportive interventions. And it is obvious that utilities is likely to be the main driver of this use case. So utilities should define the energy data formatting and reporting requirements for their energy efficiency programs. And that requirements should be consumable by APIs. And they can also take the initiative to establish an energy data repository and an automatic data intake process under their energy efficiency programs. And ultimately, at the policy level, there needs to be a standardized data format for NLC energy reporting to utility efficiency programs. And to verify and claim energy savings, there needs to be a sufficient level of confidence over the energy data generated and reported by the NLCs. So therefore, standards need to be developed for testing native NLC energy monitoring accuracy and for specifying application-specific accuracy requirements. So each of the three use cases we have discussed so far has its own unique market barriers and technical gaps. However, there are also overarching gaps common to these use cases and potentially even other use cases. And these gaps are the lack of data requirements, data format and granularities, like you have already heard in all three use cases, they are not fully articulated for each interoperability use case. And the lack of project development examples for quantifying the value of a use case to stakeholders, for resolving any potential conflicts amongst industry actors implementing a use case, and for providing evidence for developing data and interoperability standards. Lastly, the gap related to product development. Products and systems are not designed with the foresight for interoperability, which causes sharing and consuming data across systems a cost-prohibitive afterthought. So in order to bridge the gaps and advance the state of interoperability, we recommend the stakeholder groups with the most to gain to assume the leadership and to drive the realization of the specific interoperability use case. And this will hopefully create a virtuous cycle as shown in the diagram, where the stakeholder group that takes the driver's seat can sponsor pilots, demonstrations, and case studies, which help quantify values and identify best practices. These then become the supporting evidence for developing standards and policies. And with standards and policies in place, customer and market demand will increase, thereby realizing the interoperability use case. And the industry can move on to the next high impact use case, repeat the cycle again and again to realize more and more interoperability use cases.
Thanks, Xiao. And so in this report, we have explored three use cases for interoperability. The report can serve as a guide for anyone who needs to specify network lighting control interoperability on a construction project. It is essential first to describe what is needed for each particular use case, whether that might be one of the 3 use cases explored here or other use cases that you've developed in a similar manner. After doing that, the needs identified in each use case can guide the development of technical specifications of system capabilities and features. In the research report, a section just before the conclusion outlines the steps to analyze other use cases in a similar way, like we've done here. Also, Appendix E shows how to translate this analysis into technical design criteria. Interoperability is essential to the DLC's mission of optimizing energy use by enabling interconnected solutions with a focus on quality for people and the environment. We intend to use the research findings as a cornerstone to advance the state of NLC interoperability by implementing a multi-year phased strategic plan to recognize systems that are listed on the Network Lighting Controls Qualified Products list that support various aspects of interoperability. We will work with current and new DLC stakeholders to address the various challenges identified in this research and to implement key interoperability objectives based on the value of various use cases to various stakeholders. If you're interested in learning more, here's the link to the full research report under the Resources heading at designlights.org. The report has roughly 20 pages of text plus several appendices. Of particular interest, the conclusion contains a list of ways that various stakeholders can support these 3 interoperability use cases. A few additional resources will be posted soon. A summary of the information in the report will be on the DLC blog, also under the Resources heading. From this webinar today, the slides and a recording will be posted under News and Events. The DLC technical requirement for network lighting controls that qualify for incentives from DLC member utilities is updated each year to keep up with the rapidly evolving market. This year's update will be published later in June under the Lighting Controls heading, with the main changes focused on interoperability and also on cybersecurity. We appreciate the generous support of Natural Resources Canada, which co-sponsored this work along with the Design Lights Consortium. Also, many thanks to our panelists today for the work that you've done and presented here. Since you're curious enough about this topic to still be paying attention, you might also want to check out the brand new Integrated Lighting Campaign from the United States Department of Energy Better Buildings Program. This new program will kick off next week on June 10th on the 3rd day of a 4-day online summit. One of the main topics will be the first use case that Ron presented here, about integrating network lighting controls with other building systems, such as heating, ventilation, and air conditioning. You can find it by Googling Better Buildings Summit 2020. That concludes our presentation. And now I'll check in with Dan Hannigan from Energy Solutions, who has done a great job over the past year at keeping this project on an ambitious timeline, and today has been monitoring the questions.
Yeah, thanks, Levin. Can you hear me all right?
Yes.
Great. So we did have a couple questions. The first question on our list is regarding the first use case we covered. And Gabe Arnold asks, can you say more about why this use case is focused on sharing data through an API? Do you see a role for BACnet and potentially other systems to share data? Are there advantages to an API that would make it superior to other solutions? And I think, Ron, you might be the best person to answer that.
Yeah, thanks, Dan. That's a great question. Thanks, Gabe. So when we were talking about doing the research on this use case, we were looking at, well, what are systems doing today? How much integration is there between the lighting system and, say, a building BACnet system versus a lighting system and an IP system that shares data across some sort of web services? And we found that more of the systems were integrated using IP and not BACnet. So we initially looked at the API as a mechanism for those systems to share data. But with more and more systems adopting a common platform in the building, BACnet or other types of networking within the building can provide a platform where these data models can share information directly amongst the system on the same communications network, and thereby negating the need for the API. So the API is sort of the intermediate step. The ultimate, and the project that I mentioned during my talk is directly using BACnet for refrigeration, lighting, and HVAC and other systems. And there's a common infrastructure that all systems have to play nicely and adapt into. So I think there is tremendous opportunity there to reduce cost and provide value from a common single seat front end monitoring system, an alarming and alerting system, as well as data sharing between the systems. So I think one is sort of an intermediate step, and the ultimate goal would be a more peer-to-peer fashion on a simple control network. So hopefully that answers the question.
Great, thanks, Ron. We had another question come in regarding the third use case we covered, and it asks, why should energy reporting require 15-minute intervals if there's no status change? How about reporting every 24 hours of stored historical data or anytime there is a status change of load demand? I think Yao might have info to respond to that, but I'll open it up to our other panelists as well.
Yeah, that is a great question and a great point. The use case example that we use is constructed based on what we have seen, what's out there, although not quite the full-blown interoperability, right? And 15 minutes is the most common requirement that we have seen. And we are not, in this study, we are not trying to say this example should be the way moving forward, but mainly the key point for this particular use case is that there needs to be a consistent reporting requirements, right? So if someone is reporting every 15 minutes and other people are reporting on an event basis reporting, then when the utilities or whoever who has developed this automatic data intake process to analyze the energy savings in an automatic fashion, they will face the challenge to harmonize all these different data intervals requirements intervals and format, which will cause a lot of unnecessary difficulties in terms of processing the data. So the main point that this use case is trying to make is that as long as there is a consensus-based data reporting and formatting requirement that is acceptable for everyone, we can move this use case along much faster so that everyone knows and has a way, a kind of a standard or best practice to follow and to design their programs, to design their systems, and to design their analysis accordingly in a more unified way. And I hope that answers your question.
And Dan, if I could jump in with another thought on this. One of the other opportunities for the reporting side or the monitoring side relates more to real-time monitoring of energy usage, especially when a facility is considering putting in distributed energy resources, such as cogeneration or solar or other types of on-site energy production, and where they're trying to manage the energy usage within the facility in a more real-time fashion. So going into the future, we're going to see the relationship between the DERs and the facility, primarily HVAC and lighting, and maybe plug load as well, having to interact with each other in more real time. Now, that's not for historical reporting, but that's actually for real-time control and use of backup generators and monitoring a transactive energy model for when it's more efficient to run your own internal generation than it is to buy it from the utility. And utilities are facing this issue as well with the growing demand and installation of distributed energy resources. It becomes sort of a two-way model, managing the load and managing the reporting of that in sort of a real-time basis. So I'd see that as something that may come down the road where this use case could have some tremendous benefit.
Yeah, I might add a couple things too. You know, there's just an important difference too between what the logging interval is and what the reporting interval is over the communication network, right? And so I think there's most common, you know, 15 minutes is most commonly talked about in terms of the logging interval, right? You should be storing data every 15 minutes for cumulative energy or power demand. But depending on the use of that data, I might not need to analyze that data but once a day, right? So maybe I could wait, you know, every 24 hours to collect that 15-minute interval data over the network to do my analysis. But then there are other use cases where I need that data much sooner, maybe in something more real time. I think that's more along the lines of what Ron's referring to. So at the end of the day, I think this is also a question about managing, you know, network constraints, if you will, right? And what you're able to do on the network may affect which route you take or how often you can collect the data.
Sure, and as a follow-up to that, a follow-up question to that kind of same line of thinking is, what is the best way to get utilities and utility program managers to consider some of these different types of energy reporting that are either real time or are based on state changes rather than this you know, perceived older method of constant interval reporting?
You know, again, to me, it depends on just when does the data need to be analyzed for what purpose. And the idea that event data produces less, or event reporting produces less data is not necessarily true. It depends on, you know, how the system is configured, you know, what triggers the sending of data. We've seen systems that when they're configured to do event reporting, maybe don't have the granularity to say I'm only reporting energy data when energy events, when it changes, right? They're looking at a whole set of events and reporting all the data whenever any of those things changes, and that can result in much more data, much more network traffic, right? So that's not necessarily, you know, an improvement there around managing network bandwidth.
Yeah, if I can add, there's a little bit of the if you build it, they will come model. I think in utility incentive programs that are looking at how to manage the grid operations, if there were reliable real-time energy reporting data, especially for large institutional, large loads or aggregated loads from many buildings from one customer, there would be an incentive to say, hey, tell us your predictive load, and we'll design a program to help with the energy savings model. But some of that comes from not only you know, public policy, but from the rate setters and from the regulators as well. So there's an interaction between the utilities and the regulators and the policy makers as to how do you do that and how do you make it fair for large and small facilities to take advantage of that. So there's quite a complex scenario. But I think once the general model says, yes, we can do this, we can do it in second accuracy or, you know, sub-minute accuracy and reliability, then I think there's going to be more uptick in the way to do that. And I think OpenADR, the OpenADR Alliance, is looking at that as some new capability with their two-way model. So we'll see how that transpires. But first step, let's make it available. It's pretty simple for the lighting system to do that.
Well, and when you look at current use cases too, I mean, you know, for the use case described for energy reporting here, for the example for that use case of utilities providing energy efficiency incentives, right? While that might want 15-minute data, that's not requiring 15-minute data in real time. Again, you could log that data and then, gather it up over the network once a day and maybe do that for a month, and the utility could look at that data to verify that the efficient system you installed is actually, delivering the energy savings. So that's not a real-time data over the network use case. And then on the other end of the spectrum, even the future grid, service use case is not requiring the system to continuously send real-time data communicating, energy consumption, right? It may be waiting for a request. Hey, and now I got a request. Now I need to know really quickly when you're gonna what your flexibility is in an hour, in a minute, next day. But that's an event triggered activity, right? That doesn't require real-time, constant streaming of energy data. And then on the other end, verifying, maybe you're only verifying during the event, maybe at the conclusion of the event, right? So also not requiring, real-time streaming of energy data.
Thanks. Let me jump in and move to a different question that someone asked about how will this impact testing requirements? So I would like to hear from Michael. As standards are developed, how would you expect that they would be tested in terms of demonstrating interoperability between systems for these use cases?
Well, I would guess they would continue to be done in similar ways to the way they're being done today, which is some combination of certification testing and so-called plugfest, right? Certification testing often, is used to validate your ability to be on it, get on a network, join a network, communicate on the network. But then stop short of, looking at addressing specific data types and specific use cases, and that's kind of the role of plugfest, if you will, right? Those kinds of environments where you set up a architecture for a given use case, and different vendors can, plug in their device into the right slot, in that architecture, and the use case can be evaluated and verify that the different systems, can implement it. Those practices, have long been in place and continue to get, I think, more sophisticated. And that's how you, I think can meet the new use cases or the emerging use cases here. In particular, where the interoperability is facilitated, directly, right? So in Ron's example, at the backnet level, if you will. If interoperability is facilitated via an API, then you're still writing some code, and that use case is implemented on a case by case, building by building basis, right? And so that needs to get planned in, to the building development. Maybe even in that realm, there's interesting, to me, developments where maybe people will start to more rigorously have a common design environment for a building during its design or retrofit and deployment and operation, which even for the API scenario might allow you to, quote, simulate, right, building interoperability before and simulate the use case at the API level before you actually push things out to the systems in the actual building. So for some people, this is kind of the so-called, digital twin implementation or idea.
If I could add to that, Levin, just one thought. I'm not a big fan of plugfest, like Michael mentioned. I'm much more of a fan of better specifications that define the interoperability requirements and give a self-testing procedure so that you can model what the requirements are yourself, and in essence, self-validate your interface meets the model. So we're not quite there yet on the models, but there are entities that are working to develop those interoperability models by defining very detailed points lists and object definitions and what I refer to as an equipment profile. So we could have a lighting profile that says these are all the required and optional points that are defined as part of this interoperability project. And there's no question as to what the data is, its range, resolutions, offsets, minimum, maximum, alarming points. All of that information can be very well defined. And then there's no question, you plug it in and it's going to work, and you test it yourself against a golden image. So there are multiple ways of getting that testing and validation done. But I think, sort of what Michael was alluding to, we do need better specifications. We do need better standards in order for these systems to work together.
Yeah, that to me is kind of the trade-off of the better your spec is, the higher chance, if you will, that the spec can be designed to, right? There's still always some chance that someone didn't implement it correctly and it might not work, but the better the spec is, that manages, that is one way to addressing that risk.
Thanks. Well, that sounds like a great note to end on. I hope everyone here is inspired to go and develop some standards. So thank you very much for listening, and that concludes our webinar.
Thank you, Levin.
Thank you. Bye-bye.
Thanks. Bye.
Bye.